Okay, good afternoon everyone. My name is Satya Lotan and this is we are from Indonesia. And first of all, I'd like to tell you how the idea of our research came up. I believe a lot of us came from different countries and we came here by using transportation which requires fuel. I believe that even if we are from different countries, fuel is mostly used for transportation, and there are two most common forms of fuel, which is diesel fuel and gasoline. In our point of view, diesel fuel is much better than gasoline because of its better fuel efficiency and higher energy content.
Both diesel fuel and gasoline are made of petroleum, a non-renewable energy source. So a lot of usage of diesel fuel will cause a shortage of petroleum. In our country, which is Indonesia, at 2010, the usage of diesel fuel itself has reached 34.71 million liters, at which 52.27% of it, which is 18.14 million liters, are usually for transportation. According to Nugroho a researcher from Indonesia, in 2006, the world's petroleum stock will only last for 30 to 50 years. Can you imagine 22 years from now we found ourselves unable to use transportation which requires fuel? That's why we need a new alternative fuel source that is renewable. One of them is biodiesel.
This is an example of the existing material to produce biodiesel, which is soybean. Biodiesel is made from oil, and in this case, soybean contains high oil, so it is used to produce biodiesel. However, in Indonesia, and I also believe some of you use soybean as food supply. So can you imagine if there will be a big argument between people who want to use soybean as biodiesel and people who want to use soybean as food supply? Therefore, we would like to find another source, which is we want to make an alternative energy using extracted oil from Parkia timoriana seeds as a biodiesel.
This is the Parkia timoriana tree, fruit, and plant. Indonesian people use the Parkia timoriana seeds as medicine to cure diseases such as ulcer, diarrhea, and stomachache. However, nowadays the Parkia timoriana is abandoned in Indonesia, so it brings a possibility of becoming extinct. Therefore, by adding a new function, which is making a biodiesel out of it, we hope that it will prevent it from becoming extinct. Although Parkia timoriana may take some time to grow, however, when it produces its seed, it is large in quantity. So how exactly do we make these seeds into biodiesel?
First, we'll need to prepare the seeds for the oil extraction. To increase the yield of the oil extraction, we'll dry and grind the seeds. First, we'll roast the seeds for 1 hour at low up to medium fire, and this causes a 10.1% decrease in mass. And then we'll remove the seed coats by using plier. This causes 56.8% decrease. And then we'll blend the seeds to get a larger surface area and break glycosidic bond if it is present on the seeds. We'll dry the seeds to remove the water content by using oven at temperature 100 degrees Celsius for 4 hours, and this causes a decrease 58.1%. And if the oil extraction is unable to be done on the same day, so it needs to be stored in a special container, a tight container filled with a dehumidifier, at which the active ingredient is calcium chloride. Calcium chloride is a hygroscopic substance and can attract the water molecules from its surroundings.
Now the powders are ready for oil extraction. So first we use solvent extraction method, that is solvent extraction. The solvent that we use is anexane. So first we pack the powders into the filter paper and put it inside the chamber. Then we put anexane inside the round bottom flask. The anexane is then heated, and through a certain chamber it will be evaporate and then be condensed so that hot anexane may go down. Then the anexane will collect the oil until a certain limit and pour it down back to the bottom flask. We do so for 85 grams of powder. We do so for 44 hours. the temperature to evaporate and exit is 70 degrees Celsius. Then we purify the oil by using filtration so that any remaining powders that may have escaped from the filter paper may be filtered, and then using the distillation method to separate and exchange from the bio oil of the timoriana seeds. The process takes 1 hour, and then we can get our bio oil which have a decrease of 94% based on the seeds.
And now the oil is ready to produce biodiesel. However, we need to test the free fatty acid content of the biodiesel, of the oil, because if the oil has high FFA content or free fatty acid, it will need a pre-treatment, and if the oil has high FFA, it will cause an unwanted solidification reaction, which will produce soap and decrease the yield of the biodiesel. We test the FFA content by using titration method, standard sodium hydroxide 0.04 normality, pH method, and we found that the FFA is 2.54%. So we will need a pre-treatment to decrease the FFA, which is esterification. For one process of esterification, we use 7 grams of oil. We react them with methanol in the presence of sulfuric acid, 3% of oil weight or 0.21 gram as the catalyst. We react them for 2 hours at temperature 65 to 70 degrees Celsius and stirred at 450 rpm. The mixture after esterification is poured into separating funnel, and you will find that there are 2 layers. The top layer is methanol, sulfuric acid, and water, while the bottom layer is the methyl ester and the unreacted triglyceride. We do 3 variations to decrease the FFA content. The mass ratio of oil to methanol is found to be 1 to 2, which is the optimum one to decrease the FFA. And there's a total decrease 94.6% in mass. And now all of the esterified oil have been lower than 1% the FFA. So we can do trans-esterification. For one process of trans-esterification, we use 5 grams of esterified oil. We react them with methanol, 7.5 grams or 1.5 times of oil weight. In the presence of sodium hydroxide, 1% of oil weight or 0.05 grams as the catalyst. We react them for 1 hour at temperature 65 and 70 degrees Celsius and stirred at 450 rpm. Again, we pour the mixture after trans-esterification into a separating funnel, and the methyl ester or the biodiesel is found to be at bottom layer, while the top layer is glycerol. So we'll just take the methyl ester. However, at both layers, excess methanol and soap may be present in few quantity.
So we have to purify the biodiesel first. So first we pour the biodiesel into the separating funnel, and we also add hot distilled water into it. We then shake it so that the water may dissolve the soap inside the mixture. And then since water is denser than biodiesel, we only take the biodiesel layer. Then we add dichloromethane to the biodiesel layer so that the dichloromethane may dissolve the biodiesel. We filter it again so that any solid soap remaining may be filtered, and then we heat it for 3 hours so that the dichloromethane and excess methanol may evaporate. There is a decrease of 97.4% in use.
Now we'll test the biodiesel. First, we'll test the energy content of the biodiesel by using bomb calorimeter. It is found that the energy content of the biodiesel made from Parkia timoriana seed oil is 38.2 kJ per gram, while the general biodiesel is only 37.8 kJ per gram.
Then we use gas chromatography, mass spectrometry to know its chemical contents. We found that there is 87.08% of biodiesel, while 12.92% of impurities, which is unwanted extracted substances from seeds and the process also.
And now I'll show you how the mass of the Parkia timoriana seeds decrease at each process.
So in conclusion, 1 kilogram of seeds can only be turned to 26 grams of biodiesel, which the yield is 2.6%. The optimal mass ratio of oil to methanol in esterification to decrease the free fatty acid is found to be 1 to 2 from the 3 variations done. The energy content of the biodiesel is 38.2 kJ per gram. The 87.08% of the mixture is found to be biodiesel, and may need further purification.
And for the future research, we hope that we could find the optimum experimental conditions of esterification and trans-esterification, such as the temperature, time of reaction, ratio of oil to methanol, amount of catalyst, and stirring rate. And we hope to be able to separate the biodiesel from the impurities by using membrane separation technology. And we hope that we could determine the important characteristic of the biodiesel, such as seton number, viscosity, cloud point, pour point, flash point, ID number, AC number, and other important characteristics. And in this project, the seed codes are considered as waste. So we hope that in the future we could find the usage of the seed code for another possible purpose.
I hope that our research will be useful for the future. Thank you.
Okay, thank you very much for the very interesting presentation. So, do you have any questions? Please.
I think there are two factors we need to consider. First is the energy content of the biodiesel, and second would be the ratio of conversion from the source to biodiesel. I think you compare the first with the general biodiesel, but have you ever compared the ratio of conversion to other methods of producing biodiesel?
I'm sorry, we haven't done it yet, but we will take it for further consideration in our further research.
Thank you for the suggestion.
Yes.
Do you know the other plants' biodiesel yield? And is your plant is better than them? Or
Can you repeat that?
so how was your research's biodiesel obtained yield compared to other
The yield.
Yeah.
Well, actually, our yield is very low because the seed coat itself containing 50% or more of the seed's mass, and we actually chose this plant because it is rare and since it's abandoned and people doesn't know the functions. It is rare in Indonesia, so we decided to add a new function so that maybe it may turn popular because the people want to produce the Parkia timoriana for more biodiesel research. Thank you.
And comparing this yield with the yield of another biodiesel projects, how big is your yield? Comparing with other biodiesel projects, how big is your yield?
The yield of other projects.
Yes, from the beginning, from the seed to the final fuel, biodiesel.
Our yield.
Yes, your yield, and there are also several projects all abroad that provide that to produce such a biodiesel, such fuel.
We actually haven't researched other biodiesels yield, but ours is actually 2.6% from the first series.
In your process of making biodiesel, it took like 8 different processes, and it included usage of electricity. And can you do you have a slight idea of how much energy you used in the process of making that biodiesel?
So the total energy produced compared to the making is actually 1%. So we have a very much loss in this making. However, we believe that in an industrial scale, which we can process many seeds at the same time, we will gain profit instead of loss.
And we also hope that we will find the optimum experimental conditions.
A very short question. So, as I understand, yield is not so high, unfortunately. Yes?
Yes.
But my question is it possible to just use these seeds as fuel? Maybe to burn it in furnace and produce other energies, I don't know, Because maybe
So-
it can produce more energy.
You are asking if you can burn the fuel or
No. If you can burn seeds in furnace, for instance, to produce energy, I don't know. Because
burn the
it's
seeds
a
Yeah,
red
we can-
material and maybe.
burn directly the seeds into the furnace.
Yeah.
So
Is it
just
possible?
burn the seeds and well, at first we experimented the seeds by burning and the seeds burn for some time.
So they burn in principle. So can they be used as fuel, for instance?
Because the chemical composition is different, so we cannot use the seeds directly as a fuel. So we need to react them until by becoming biodiesel.
But maybe they can use for production of synthesis gas, like some wastes, I don't know. When you mix it with some fuels like coal or oil, and then to burn it and to produce some gases which will further can be used for synthesis.
Yeah, maybe they can, but well, since our main focus is to produce
Yeah, I
biodiesel.
understand. It's just for my information.
Thank you for the suggestion.
Thank you very much. So